Welcome to another episode of Logic Made Lucid with Dr. Jacob Waldenmeyer. In the previous episode, we explored probability and we looked at the logic behind probability. We did a little bit of mathematics related to probability, and now we're going to examine statistics, which expands some of the reasoning behind probability. The purpose of statistics, what we're trying to do, is that we're trying to address situations where it is impossible or difficult to examine every member of a usually large group. And when we can't do that, statistical methods enable the formation of an estimation. And in other words, we are doing what we had discussed earlier in the series. We are creating a strong inductive generalization. And this is going to be much more mathematically based than previous inductive generalizations that we have explored. When we are doing this, we are basing that generalization on a sample from a group, from a population. So, for example, we could statistically analyze the proportion of herbivores to carnivores in a region. We might take a sample of that and then make a generalization or an estimation based on that sample of the whole population. We might be wondering about the number of Frenchmen under 30 who drink alcohol. We might be wondering about the favorability of a ballot issue among a population of voters, right? Obviously, in all these cases, you can't look at or interview or examine every last member of these populations, at least not logistically or not feasibly, and so we take a sample and we estimate from there. We could also ask about, say, the average duration of a lithium battery. Let's say there's a manufacturer that produces many lithium batteries. You can't possibly look at the average duration of all of them, so you take some of them and then you extrapolate from that sample what you can expect the average duration of a lithium battery in the whole population will be. When we are taking those samples, there are certain important criteria that we need to follow. Sampling, the way we take samples, I'm reminded of a common phrase in coding where we say garbage in, garbage out, right? If the sampling is done poorly, then all the remainder of your results will not be accurate. It's going to spoil the remainder of your analysis. So the sample that you're taking must represent the whole population. All right, we can kind of depict it like this in a sense. Now, this isn't necessarily the best depiction because really the sample should be spread out. So we're going to look at some of the conditions for a good sample or meaningful sample. Inductive generalizations are more reliable or stronger when bias in those samples from which they are drawn is minimized. There might always be some small level of bias. There could be a large level of bias, and we want to reduce that as much as we possibly can. So how do we do that? What are the basic ways that we can reduce bias? One of them is by having a random sample. Right? Bias is reduced by a sample's randomness. And we're going to explore what that means very soon. Bias is also reduced by a sample's size. Right? So the larger the sample, the lower the bias in general. Also, the bias is reduced by a sample's objectivity, and we'll talk more about that in a moment as well. Objectivity generally relates to the idea that the way that you are collecting your data is not marred by any kind of psychological bias, for example. So randomization, right? Every member of the population must have an equal chance of being part of the sample. Right? This is what randomization means. There's an equal probability. The likelihood of any given member of a population being part of the sample is equal. So in other words, the selection method must not favor any particular attributes or any others other than the predetermined attributes of your desired population. So if you're looking for, like the earlier mentioned, the Frenchmen under 30 who drink alcohol, well, you don't necessarily want to skew your results by including more Frenchmen who, say, are major socialites, right? Perhaps people who socialize much more often will be stronger drinkers. So you want to make sure that that group is not necessarily overrepresented in your population, right? You don't want that other attribute to skew your results. You just want to get a sampling of all Frenchmen under 30, right? Okay, in that example. Randomization, one of the reasons why it's important is that it ensures that the sample represents the whole, And randomization reduces the influence of those other incidental attributes on the estimation, right? Other factors, right? Let's say, maybe people who drive less often may be more likely to drink, who knows? But that's not what we're looking at. We're just looking at some specific attributes, and we don't want to accidentally select in favor of any other attributes other than the ones that we're looking for. All right, sample size also is a way to reduce bias. When randomness is automatic, so in some cases we do end up with that. When a population is homogeneous and it's extremely large, then we only really need a small sample. Homogeneous means that it's pretty uniform throughout. Any one bit of something will look very, very similar to any other bit of something. So examples of this are blood or pool water. It's one of the reasons why a doctor only needs a small sample of your blood. They don't have to look at, say, a gallon or a liter in order to get a good sense of what's going on in your bloodstream. Same with pool water, right? By and large, it's homogeneous. You can generally expect that the amount of, say, chlorine in one part of the pool is very, very close to the amount of chlorine in another part of the pool, right? Pool water is generally homogeneous. These are some examples. Now, when randomness is not automatic, right? So when you've got a diverse or a disproportionate population, a heterogeneous population, then the sample size contributes to the accuracy of the generalization. Right? The larger the size, by and large, the lower the bias. Here I want to introduce something called sampling error, or the standard error. And this is calculated by sigma, which is a standard deviation, and we won't worry about standard deviation just yet, but I just want to include it because it's part of this formula. But I do want to direct your attention to what's on the bottom, what's in the denominator of this, over square root of n, right? So sigma, the standard deviation, divided by the square root of n. So notice, well, whenever you have some kind of proportion like this in mathematics, that means that as the denominator increases, so as n increases, then your error decreases. Right, this is one of the real realities of any kind of fraction. When the denominator increases, error, then the whole number, the entire number, decreases. Right. So look at this disproportion, this inverse proportionality between number and error. The larger the number, the lower the error. As n decreases, error increases, and as n increases, error decreases. Objectivity is that third quality of our sampling that we need to pay attention to. The way that samples are collected can bias the results, right? So this is the means by which we are collecting samples. We might have already decided on our randomness, and we might have already affirmed that. We might have already decided on a large sample size, but still we need to ask about how we are collecting our data. For when we're surveying people, for example, right, the questions could be worded in ways that elicit certain emotions or moods, or that prompt images or values, right, which then influence how the participants respond. Right? Similar, there's well, let me give you a couple of examples here. The distortion of responses worsens when the questions request estimations or judgments based on those triggers. Right? So here's some examples. Given only, if let's say I'm surveying people and I say, given only 15% of crime is violent, should laws be less cruel? So some of the wording in this question, right? I'm using the word only 15%. So I'm kind of priming the person taking the survey or responding to my question. I'm priming them to take 15% as a low number, right? So I'm saying given only 15%, I'm kind of already biasing what their response may be, right? I'm leading them towards a certain kind of response. So given only 15% of crime is violent, should laws be less cruel, right? So there, using the word cruel, I am already kind of planting, or I'm smuggling in the idea that already laws are at least somewhat cruel, and then asking whether they should be less cruel. So this is, there are emotions or moods that are applied to this, and then the only already leads somebody responding to this question to give a lower estimation of what that 15% means. Another question we could ask, which would bias our results, if I ask something like, do you approve or disapprove of this party's extreme agenda? Right? So when I use extreme and when I use agenda, those words are oftentimes associated by our population, in our society, and in our culture with kind of they have negative connotations, right? If something is extreme, the average person who is responding to a survey will feel more distant from from the idea, and they might be more likely to disapprove of some party's extreme agenda when it's described as an extreme agenda, regardless of what party we're asking about. Okay, now, randomness, size, and objectivity, we also now need to think about dispersion, right? So whenever we're getting some results from a sample, there's going to be some kind of spread, right? There's going to be some kind of breadth of a distribution. The distribution really just refers to our whole data set, right, and how they are distributed across a number of values. The range is the distance between the lowest and the highest of those values. And then the standard deviation, which we're going to get into some depth, that's really can be understood as the average distance of the values from the mean. Now you might remember from the idea of a mean is one way of understanding average. And here we're really only going to be talking about, in this episode, we're really going to be talking only about the arithmetic mean as an average. There are other ways. The other ways of understanding average include the median, which is the middle number of your set, and then the mode, which is the number that occurs most often. Later on, when we talk about normal distributions, the mean and the median and the mode really are pretty much the same number then. So we'll focus for the time being on the mean. Given a data set, so here I'll give a set of numbers, right? This is a set of numbers, and you might recognize this right away, immediately, right? Obviously, these are all of the ages of the basketball players on the Cleveland Cavaliers, right? That should have just jumped right out at you naturally, right? Anyway, well, that's where I got this data set from. These are the ages of all the players on the Cleveland Cavaliers, which is one of the teams in the National Basketball Association. Okay, now one of the things we want to do with this data set first, and it's just kind of easier to see the numbers if we just put them in order. So I'll put them in order here. Okay, so now notice we can see the range is between 20 on the lower end and 32 on the higher end, right? So the range is 12, right? Also, we can notice our size, our sample size. There are 16 players on the roster of the Cleveland Cavaliers, and we've got the ages of all of them. So our n is 16 because we have 16 ages. Our sample size is 16. Okay, now what we want to look at is our distribution. How are these ages distributed, right? So, and in other words, we want to keep track of these ages. These are not specifically the ages. These are the possibilities of the ages, right? These are where the ages will appear, and we want to look at how many of the players are at a given age, right? So that's on the left. This y-axis is going to be our n, and these x-axis, the x-axis, the horizontal axis, is going to be our values, right? Our data. So we see that there's one player who is age 20. There's one player who's age 21. There are 3 players who are 22 years old. There are 2 players that are 23 years old. And how many players are 24 years old? We've got 3 there. How about 25? 1. And then 26, 1 player. Same with 27, same with 28. There's only 1 player. Now 29, there are no players that are age 29. And then age 30, we have 1 player. And then finally, at age 32, there's 1 player, right? Almost like an outlier, but it's nevertheless important for our data set. Our sample size is only 16. Okay, well, one of the things we can do with this is we can take the mean, right? We can take the arithmetic mean. And the way we do that, you might remember from any math class you may have had in the past, you add up all of the numbers, right? And then you divide by the total number of those numbers, right? You divide by n, right? So in this case, we've got 393, which is the sum of all of our data points, divided by the number of data points, which is 16. And then we end up getting 24.6. That's simply the arithmetic mean of our population. And if we were to kind of plot it as a point on our graph, it would be right about there. Our mean is 24.6. And as you can see, just kind of visually, we've done it mathematically, we've shown it mathematically, but we've calculated it. But now you can kind of see that it does lie right about in the middle of our distribution. Now, another number that we're going to talk about very soon is standard deviation, right? So let's get kind of into that now, standard deviation. Here, what we're really doing is we are measuring the deviance or the variation between each one of those values and the mean, right? So the mean is very, very important here. And we're looking at how far each one of our data points is away from that mean, right? And then we're going to kind of average that distance or that deviance from the mean. Now, right now I'm using distance and deviation interchangeably, but it's not quite the same thing, as we'll see pretty soon. All right, here are our data points, right? Now, the first thing we're going to do in order to get our standard deviation is we're going to calculate the distance between each of these values and the mean, right? So we're really going to take exactly, we're going to take 20 minus 24.6, and that's going to give us 4.6. Then we're going to take 21 minus 24.6, and that's going to be negative 3.6, and so on and so forth. And the results of those calculations will simply look like this. All right, we've got negative 4.6, negative 3.6, and so forth. These are the distances of each one of our data points from the mean. Right? We can see at the very top and the very right, the distance between 32 and 24.6 is 7.4, because 32 minus 24.6 is 7.4. That's what exactly you are looking at right now, the distances between each value and the mean. Well, next step, we're going to square each of those distances. And there are a couple of important reasons why we do that. One of them is that we really do want to get the differences between them, and we don't necessarily need any negative numbers, because we just want to look at distance, right, as a scalar in a sense. So what we're going to do is square them, and here is these distances squared, or these numbers squared. Okay, then we're going to take the mean of those squares, right? Because remember, we are talking about the average deviance, the average distance, right? So we calculate the average of all of these numbers now, okay? And again, for the average, for the mean, we take the sum of the numbers divided by n, right? So what we're talking about here is we're talking about 164.2, which is the sum of all of the numbers that I just showed you, divided by n. Well, our n is going to be the same. It's 16, right? Just like what we had before. All right, and that comes out to 10.3, right? Now, what we're talking about here, notice we did square some numbers. So what we're dealing with here is we're dealing with sigma squared, right? Now this is sometimes called, well, always called, the variance, right? The sigma squared is 10.3. And all we have to do in order to get our standard deviation, which is just going to be simply sigma, is we take the square root of 10.3. We take the square root of both sides of this equal sign. And then we end up with a standard deviation, which is 3.2. So this is our standard deviation right here. And what that can look like if we were to plot this, our standard deviation is right about there, right? That's one standard deviation above the mean, right? Now also we can go in the other direction, right? Both of these breadths are at the end of these blue lines. That is a standard deviation above the mean, and that the length of that standard deviation is 3.2, right? And you can kind of see that the standard deviation acts as a measure of average breadth, average width, average deviation from that mean. In other words, how much do our data vary, right, from the average, right? How spread out are they? And this is, the standard deviation is our way of measuring how spread out our data are. Okay. Oh, I want to remind you also, the standard error, one of the things that we had pointed out earlier, again, if sigma divided by the square root of n, well, now we can calculate that because we have our standard deviation. It's going to be 3.2 divided by the square root of 16, which is 4. And so our standard error is 0.8. Now, this is going to be important later on when we calculate our margin of error. You may have heard of this expression, margin of error. It's very popular when we are told the results of certain kinds of surveys or collections of data. Now it's valuable to talk about normal distributions, right? So you notice that when we were looking at the ages of the basketball players, they kind of were concentrated more or less around the middle. They seemed to approach some kind of curve, right? And what we find is that for very large populations, as we gather more and more data about populations, results oftentimes begin to resemble some kind of bell, right? The higher occurrences of a certain value get concentrated around the middle. All right. In other words, the mean, right? The average, the higher frequencies are concentrated around the middle. And what we refer to this as, this was developed in part largely by somebody named Gauss, who who ended up kind of defining the parameters of this value, this pattern, right? And this is a normal distribution will follow this kind of pattern, otherwise known as a bell curve. Okay, now what's at the bottom? The x-axis. Once again, that's our range of values, range of possibilities, and then we have our sample size, or the number of constituents in a population that aligned with any particular value, right? Okay, and once again, the mean is going to be right in the middle, and then our standard deviation is going to measure the breadth, right? The average distance of all of our of each member of our population from the middle. All right, now I want to talk about something called the empirical rule. This is very interesting and very helpful when we are looking at a data set. We have taken the standard deviation. In normal distributions, the area under that Gaussian curve within any number of standard deviations can be calculated. And actually, it can be followed almost as a rule. The area within one standard deviation, what you see here is this area of under the curve of one standard deviation is going to be 68.3%. Now what that means is that the probability that any point under the curve lies within one standard deviation of the mean is 68.3%. Right? That is now. I just want to remind you about one of the things that we talked about, the probability calculus from the last episode. We had said that when we've got a probability curve, the total underneath that curve has to the total of all possibilities, the total probability of all possibilities has to add up to 1 if we're covering all the possibilities. And this is also the case for a normal distribution. The area under the entire curve is exactly equal to 1. So, but within one standard deviation of the mean, that is 68.3% of that whole, 68.3% of that one. Now the probability, following the empirical rule again, the probability that any point lies within 2 standard deviations, you see, is 95.4%. Right? So whenever you have a normal distribution, the area under the curve within 2 standard deviations from the mean is 95.4%. Now this might remind you of other occasions where you might see statistical results, like for example when people are measuring intelligence, right, or IQ. Then sometimes people have said, somebody is very smart or has exceptional intelligence or something when their IQ is, say, 2 standard deviations above the mean, right? You might have also heard people talk about percentile, right? And we'll get to that in a moment as well. This is related to the empirical rule, right? And so on and so forth. If we want to go 3 sigmas away, in other words, 3 standard deviations away, then we're talking about 99.7% of the population. Standard deviation of 4, 99.9% of the population. You may have heard of, if you've been involved in production or manufacturing or quality control, you may have heard of the expression 6 sigma. Well, that means that we're talking about making our product reliable to 6 standard deviations, right? So in other words, we're talking about 99.999, something like that, percent of our production should meet specifications, right? So this is what we get the idea of a 6 sigma. We want to be manufacturing very efficiently, and we want there to be very, very few errors in our production. Z-values are another way of looking at the area under a curve, except now instead of looking at values in between 2 points in a standard deviation, we're looking at the area under the curve, the probability within a range, up to a specified number of standard deviations, right? So we're looking at the area to the left of a point, right? The total area to the left, not simply within 2 margins on the right or the left. We're looking at everything on the left up to a point, right? So when you've got the mean, the area under the curve to the left of that is going to be 50% of our total, right? So the z at that middle, right? The z at 0 standard deviations is going to be 50% of the area under the curve. And you can kind of see this visually as well. Well, when we want to do the z value at 1 standard deviation, again, we're looking at the total percentage of everything that's under the curve to the left of that bar, or that of 1 standard deviation in this case. And in that case, z is 84.13%, right? How about the Z at 1.57 standard deviations? And there we have 94.18%. Now these may seem a little bit arbitrary, but they're actually calculable. And there actually are, and you can actually look this up. There's, I think, a website called z-table.com where you can look at all of the Z values for any given number of standard deviations above or below the mean. So Z values are very helpful when we're trying to measure accuracy or when we're trying to measure confidence levels, right? How confident can we be, right, with our results? Remember, we are in all of these cases we are estimating the extent to which our sample describes the population, the whole population, right? Again, large populations typically follow normal distributions. We want to ask how accurately will our sample represent or resemble the population, right? That's what we are asking about when we're checking for confidence levels. So margin of error, again, there's that concept that you may be familiar with. Within what two numbers can we be pretty confident our actual figure is, right? So how likely? That probability is the confidence level, all right? We're going to use our confidence level to determine the margin of error. Now the confidence level is something we can sort of typically choose, say a 95% confidence level, right? We want to say we want to be about 95% confident that that our results or that the true population is within this certain kind of margin, right? If we want to be 95% confident, well, there's a way to measure that. And so we can measure our confidence interval based on that standard, based on that condition. And here's the formula. And I'll explain this formula a little bit. This X with a bar over it, that is quite in a straightforward fashion, that is the mean of our sample population. Now you remember earlier I used the symbol mu, and I'm sorry I forgot to explain that little funny character that you saw. It looked a little bit like an M, but it also looked a little bit like a U. That's actually the Greek letter mu, and it's oftentimes it usually refers to the mean or the average of a population. But when we're only talking about the mean of our sample, then we use that X with the bar over it, right? So X with the bar over it is our sample mean. You remember earlier when we were talking about the basketball players, the ages of the basketball players in the Cleveland Cavaliers? Well, it would have been more accurate to talk about our sample mean. But of course, at the time, we were talking about the whole population of the Cleveland Cavaliers. And we can look at the whole population of the Cleveland Cavaliers. So we might use mu for that. But when we're only talking about the sample mean, the mean of the sample, we would use X with a bar over it. Okay, now the rest of the formula. Our sample mean plus or minus, and here's what's good. You'll notice this looks like what we've seen in the past as a margin of error. Plus or minus the Z value when we want a confidence level of 95%, Z value times, and you'll notice that sigma over square root of n again, right? Remember, this was our sampling error, right? We've seen this before a couple times, right? All right, just to point that out, that it's relevant now to what is going to become our confidence interval, right? So our sample has 16 measurements, so we already know n, right? We actually we already have all of these numbers already, so we can easily calculate our confidence interval. Our mean was 24.6. Our standard deviation was 3.2, right? That's the sigma that we see. Well, that means, and we're choosing 95% confidence level, so that means our confidence interval at 95% confidence is 24.6, which is our mean, plus 1.96 times sigma over square root of n, right, which is 3.2 over square root of 16. Now that 1.96, that again seems a little bit arbitrary, but that is the Z value at 95%, right, when we want to be 95% accurate. Okay, well, we can easily just, calculate this, right? We got 24.6 plus or minus 1.57, right? This is what we end up with. And 1.57 is going to be our margin of error, right? We've got plus or minus 1.57, right? Now what that means, taken all together, what that suggests is that there is a 95% chance that the average age of American professional basketball players is between 23 and 26, right? All right, now, This is a little bit interesting because, and you may be wondering why we're taking this step. And it's a bit of an inappropriate step, and we'll see why in a moment. But what we've done is we've taken the mean of a particular team, the Cleveland Cavaliers. We've looked at the average age of those basketball players, and then we've taken the standard deviation of that, and then we've said that we want to be about 95% confident that our sample, which is all the Cavaliers, represents a larger population. Now, we could say the larger population is all the players in the National Basketball Association, all the basketball players in the NBA, all of these professional basketball players, right? So, in other words, the average age of American professional basketball players is between 23 and 26. Well, you may remember earlier on when we were talking about randomness, right? Remember, garbage in, garbage out. Garbage in, garbage out. That means that if your data are not collected with true randomness, then your results might not be accurate. Your results are going to be contaminated by that lack of randomness, right? So let's take a look at what actually is the case. What is the actual average age of NBA players? The actual figure, 26.3, right? Now we've said that the average age is going to be between 23 and 26 with about 95% accuracy, right? Okay, within that margin of error. Okay, well, we knew that our margin was not 100% certain, right? So there's always the possibility that the actual average could be outside of what we've said our margin of error is, right? Because again, we haven't said 100%, we've only said 95%. But at the same time, this does seem, a little bit off. I thought we did our calculations fairly accurately. So there might be more explanations for this inaccuracy. And I've kind of already just described one of those explanations for the inaccuracy. Our sample was not random, right? It was not really a random sample. It comprised the ages of only one team and all the ages of one team, right? That is a defined and discrete subset of the NBA, and that is not random, right? If we wanted to estimate the average age of an NBA player of that whole population, what we should have done is we should have had a random sampling spanning that population. We should have taken samples from all of the different teams at random, not just one team. And then we would have had a random sample, but we have not had a random sample. We've only had one team, and that team was the Cleveland Cavaliers. Now, we can draw a conclusion from the results, though, right? Even though we can't make that leap between saying that the mean and standard deviation of that one team represents accurately the mean or standard deviation of the whole population, we can't really take that step. It's not a valid step to take. However, we can say that the average age of the Cleveland Cavaliers basketball players is lower than the average age of NBA players, right? And again, Cleveland Cavaliers is a subset of all the NBA players. But yeah, we saw that the average age of Cleveland Cavaliers seems to be lower than the average age of NBA players. So we could say that this year's Cavs is a young team, right? Comparatively, it's a relatively young team. All right. So I hope this has been a very helpful overview of how we can analyze data and then use data from a sample to then draw some kind of general estimation, make a strong inductive generalization or inductive argument that will give us information, likely information, that describes the overall population. Statistics is enormously helpful in doing that. It's extremely versatile. So I want to point out the normal distribution suits a wide variety of applications, right? It's useful not just in studies of human and animal and plant populations, which we can see, I hope, that these are typically large populations from which we need to get a sample, and then we use that sample to make some kinds of estimations about the general population. It's useful not only in human, animal, and plant populations, but also it's useful in biology, and like cellular biology, not just human, animals, and plants, but in biology in general. We can use normal distributions when we're talking about bacteria, for example. We can talk about genetics using normal distributions when applied appropriately. Thermodynamics, particle physics, the normal distribution shows up in all of these different fields. It's really very, very interesting the way the math works out and the way the math fits many, many different circumstances. There are lots of other ways in which math does that as well, which we could talk about in other episodes too. But certainly the normal distribution is extremely versatile there. So I hope you've enjoyed this episode. In our next episode, we're going to start to talk about scientific reasoning. We look forward to seeing you then.